Welcome to this video in A-level chemistry where I look at mass spectrometry. Firstly, let's look at a few principles that are important to understand when looking at mass spectrometry. Firstly, charged atoms. Charged atoms are called ions. There are positively charged atoms called cations and negatively charged atoms called anions. So we have examples of two atoms underneath. First one is sodium. It has a mass number of 23, an atomic number of 11. Okay, so the atomic number of 11 tells us that this atom has 11 protons. And each proton is positive. So it has 11 positive charges. And the relative charge on each proton, if you remember from the last video, is +1. Now, in a neutral atom, it will also have 11 electrons, which are negatively charged. So 11 plus 1 charges and 11 minus 1 charges, the net charge will be 0. If this atom then loses 1 electron, so it has 10 electrons, then it will have an overall charge of +1, because it will have 1 more proton compared to electron. It now has 11 protons, so 1 extra proton, and so it has an overall charge of +1. If it now loses another electron, and in this case the number of electrons in sodium will be 9, you'll have a charge of +2. Let's look at chlorine. Now sodium is a metal, and at GCSE you've learned that metals lose electrons. You've also learned that non-metals like chlorine gain electrons. But in a mass spectrometer, any atom can lose electrons, even a non-metal atom. So for chlorine, it has 17 protons, and in a neutral atom, it has 17 electrons. If we lose 1 electron, it has an overall charge of +1, so it will become a cation. In order to become anions, atoms need to gain electrons. And in this case, sodium normally does not gain an electron, chlorine does. So chlorine, because it's a non-metal, will gain an electron, and if it has 18 electrons and 17 protons, the overall charge will be -1. And it's important that you understand how to calculate the overall charge of an atom. We've also looked in previous videos at the atomic mass number. And that's the number of protons plus the number of neutrons in the nucleus of an atom. Here I'm going to discuss something very different, which is the relative atomic mass. The symbol is Ar. The definition is the mean mass of an atom of an element divided by the mean mass of one atom of carbon-12. So here we're comparing the mass of one atom of a particular element compared to the mass of carbon-12. So for example, we know that the relative atomic mass of a helium is 4. And if we compare one atom of helium to one atom of carbon, then the mass of helium will be 3 times less than carbon. So that's a mass of 4 compared to a mass of 12. And that's how relative atomic masses can be determined by comparing the masses of a certain quantity of a substance, of an element, comparing that to the same quantity of carbon-12. The relative abundances are taken into account when calculating relative atomic mass. I'm going to come back to this point when I look at an actual mass spectrum. It's also important to understand that if you have a molecule, the definition changes to the mean mass of one molecule of an element or a compound divided by the mean mass of one atom of carbon-12. So here we're changing the word atom for the word molecule. And this will give you the relative molecular mass. It's also important to understand what isotopes are. So isotopes are atoms of the same element with the same atomic number but a different mass number. And in this case, if it has the same atomic number, this refers to the protons. The same number of protons. A different mass number, and this refers to neutrons. So it has a different number of neutrons. That's why the mass number is different. So the number of protons and electrons are not affected here. So different isotopes always of the same element will always have the same number of protons, because it's the number of protons which determines the type of element. The electrons will be unaffected, so they should have the same number of electrons unless they have become ions. In this way, because they have the same number of protons and electrons, they'll have the same chemical properties. Because they have a different mass number, though, they will have different physical properties. For example, melting point and boiling point. And we know, for example, if we have an element with a larger mass, let's say an atom with a larger mass, then there's going to be a stronger forces of attraction between atoms, and it's the same for molecules. And then in this way you can have a higher boiling point and a higher melting point. So the mass number will affect the physical properties. So let's look at why we use a mass spectrometer and how it relates to the points I've mentioned previously. Firstly, a mass spectrometer can be used to identify isotopes of an element. Also, it's useful to determine the relative atomic mass or the relative molecular mass. And here, relative atomic mass, or RAM, is AR, and MR is the relative molecular mass there. Okay, so these are the symbols we use. It's also important to understand that mass spectrometry can be used to identify chemical groups in molecules by looking at the fragmentation pattern. You will learn more about this as you progress through your A-level. We're not going to cover this here. See an overall diagram of a mass spectrometer. It has different sections and there are different stages to mass spectrometry. You can see here that we have, first of all, a vaporized sample. So when we insert a sample into the mass spectrometer, it needs to be in the form of a gas. It needs to be gaseous. In this way, if it's atoms that we're injecting, the atoms are separate. If it's molecules, the molecules are separate from each other. In this way, they can be ionized. Then we have ionization chamber, and you can see that there. And in this chamber, you basically have an electric plate. And here we have the electric plate there. You can see that electric plate. That electric plate is positively charged. We have here also a filament. When that filament is heated, electrons are boiled off. Those electrons travel to the positive electric plate. And when this happens, any gaseous atoms or molecules passing through will be hit by these electrons, these high energy electrons, and they will ionize by knocking off electrons from the vaporized samples. We then have acceleration, and in acceleration you can see that we have a plate here. This is plate, I'll call it plate 1, and then we also have this plate 2, and there's a couple of them. So if you have a sample which is positively charged because it's been ionized and it's lost an electron, then that positively charged sample needs to be attracted towards a certain plate of the opposite charge. So these plates on this side are negatively charged, and so the positively charged sample is accelerated towards the negatively charged plates. I wouldn't worry about this plate here too much, but on the other side we have these negatively charged plates, and so the positively charged sample, after it's been ionized, is accelerating and it's going this way. There are holes in between these plates and the sample passes through this hole. Then we have what we call deflection, and you can see the first part that I've discussed of this mass spectrometer is relatively straight, but here in the section dealing with deflection, it's curved, and this is very important, as we will see later. And we have surrounding this part of the mass spectrometer an electromagnet, and the strength of the magnetic field can be controlled because it's controlled using an electric current. So here the electromagnet deflects the ionized particles. It cannot deflect uncharged particles, and that's why we need to ionize. Then we have detection here, and we basically have a plate here. When the samples, which are positively charged species, hit the plate, then what is recorded on computer is firstly where on the plate that species, that molecule has hit, and also the quantity or the abundance of the molecules that are hitting that part of the plate. And this is detected and it's recorded by computer, and you can actually print it out in a chart recorder here, or it can also display it on a screen in a graphical format. The amplifier here basically amplifies the signal on the detector in order that the signal is strong enough to be measured by the computer. So let's look first in more detail at ionization. Here we have a beam of electrons. The electrons knock electrons from atoms or molecules in the sample. So for example, if I had a species called M, which was a gas, and here I need a state symbol, then I have an electron. This electron is from this electron beam. It's going to collide with and knock off at least one electron from the atom or the molecule M. What I'm going to get is M plus gas, and it's important to note the state symbol. It's still a gas, it's ionized gas now, and we're going to have two electrons. The first electron is going to be here, is going to be the same electron which is on this side, and the second electron here has come from M. So the charges are balanced and the atoms or molecules are balanced. And this is the general way in which you will write down the equation to show that ionization is occurring of M. You could also have, for example, further ionization of M. M plus gas plus E minus goes to M2 plus gas plus 2E minus. So we can also knock another electron off to make a cation which has a 2 plus charge. And it's important to understand that this is a very rare event. Most of the atoms or molecules will have a charge of 1 plus. So returning to the ionization process, one electron is lost from each species, and 5% of species will lose 2 electrons, as I've shown above. So a very small amount. This results in a cation, positively charged ion. The next step, acceleration. And the purpose of this is that cations are accelerated and they all have the same kinetic energy when they enter this chamber or this tube where deflection occurs. So deflection is not according to the kinetic energy of the species because they all have the same kinetic energy. Rather, deflection depends on how heavy or light these species are. And it's very important to use the proper definition of mass to charge ratio. So let's look at what's happening in more detail in deflection. Firstly, ions are deflected by a magnetic field created by this electromagnet. Heavier ions, and here we mean ions with a higher mass to charge ratio, are deflected less than light ones, and light ions are going to be ions that have a lower mass to charge ratio. See that this path taken by this ion here in red, this has a higher mass to charge ratio, M being mass and Z being charge. So it's deflected less. Whereas the one in blue, this ion in blue, is deflected more because it has a lower mass to charge ratio. And so it's important to understand this. It's important also to understand that most ions have a charge of 1 plus. 2 plus ions are deflected twice as much as 1 plus ions. Let's explain the term mass to charge ratio in more detail. So for example, let's say I have an ion, CH4 plus. Now, this is an ion of methane entering this tube where deflection occurs. So here, methane here has a charge equals 1 or plus 1. The mass of methane equals carbon is 12, hydrogen is 1, and so it equals 16. So the mass to charge ratio is going to be 16 over 1, okay, which is equal to 16. If the charge is 2 plus, then the mass to charge ratio will equal 16 over 2, which will be 8, and that will be half. The mass to charge ratio will be halved. Okay? And this is very important. But because it has the same mass and it has double the charge, it's going to be deflected twice. So it has a lower mass to charge ratio. The mass to charge ratio is halved, so a deflection is going to double. Let's look then at the process of detection. So here, what happens is that the electromagnet is strengthened and the magnetic field is strengthened here gradually until ions of increasing mass hit the detector. Some of them, like this one in red, will not hit the detector unless the electromagnet is strengthened. Ions accept electrons at the detector because there is an electric current passing through it. And so those ions lose their charge, they become uncharged. When they accept electrons from the detector, this creates a flow of electrons in the detector, a current. That current is detected using a computer, is passed through an amplifier first because it could be a very small signal, a very weak current. And here, the proportion, the strength of the current, or the number of milliamps or amps of the current, is proportional to the abundance of each ion. So, for example, on this green dotted line, let's say we have a species M+. That species has the same mass to charge ratio, and there's many molecules of that. Okay, let's say we have 10 molecules of M+. They will all hit the same point in the detector here, provided that the strength of the electromagnet is the same. And so we can, on this point on the detector, we'll have a certain amount of current. If I now increase the number of ions of M+ to 20, then the current here will be doubled. And so the amount of current generated when an ion hits a particular point in the detector is proportional to the abundance of that ion. This mass spectrum will help us to identify isotopes. And we can tell there are different isotopes here because we've injected gaseous boron. This is an element which is a single atom. It's monatomic. And when you put this into the mass spectrum, we get an output where we have two peaks. If this was a single mass number, then we should only have one peak. But we have two mass numbers for boron. We have a mass to charge ratio of 10 and a mass to charge ratio of 11. Now, remember we said that on average, most ions have a charge of +1. And so the mass to charge ratio will also equal the mass of that species. So we have boron 10, mass of 10, mass number of 10, and boron 11, mass number of 11. And if you look at the relative abundance, and the relative abundance means that we're comparing the small peaks to the largest peak, and this peak is a reference peak. This peak is given, because it's the most abundant, it's given abundance value of 100, and all the other peaks are compared to it. And this allows easy comparison between different mass spectra. So we have the abundance of boron 10 is 23. The abundance of boron 11 is 100. They have different mass numbers. They will have the same atomic number because they're still boron. There's the same element. And so these are isotopes. So in any sample of boron from the environment, 23 will be boron 10 compared to 100 of boron 11. 23 out of 123 will be boron 10. 100 out of 123 will be boron 11. And so to work out the relative, and this is an atom, so it's atomic rather than molecular, relative atomic mass, we'll do the following calculation. So firstly, we need to multiply the abundance by the mass number. The 23 times 10, and this is for boron 10. And then we need to add it to the abundance multiplied by the mass number for the other species of boron, the other isotope, boron 11. That's what I've done here. And then we divide it by the total abundance. Now the total abundance here is not 100, it's 23 plus 100, which is 123. And if we do the calculation, we will come to a relative atomic mass of 10.8. And this is what you will see in the periodic table. And this is how we calculate the relative atomic mass. You can also calculate the relative molecular mass in the same way. But we normally do this for atoms because this allows us to work out relative atomic mass for atoms which exist as different isotopes. Let's now look at a more complicated example of chlorine. Now chlorine has two isotopes, Cl35 and Cl37. So if we add these two together, we'll have 100. So we can say that 25% or 25 out of 100 of chlorines in the environment are going to be Cl37. Most of the chlorine, or 75% of chlorine, is going to be Cl35. So whenever we have chlorine, and these are single atoms, we're considering single atoms, most of them are going to be Cl35, 75%. But the problem is that we do not see two peaks on the mass spectrum because Cl exists as Cl2 in nature. Chlorine gas, so chlorine as an element exists as a diatomic molecule. This is very important. So we can have three situations. We can have Cl35, Cl35. And this is both chlorines in the chlorine molecule that have a mass of 35. And so if we add these together, then the total mass is going to be 70 of this molecule. We can also have Cl35 and Cl37. And if we add these together, the mass of this molecule is actually going to be 72. We can also have Cl37, Cl37. And so the mass of this is going to be 74. And so all these possibilities do occur because we have Cl35 and Cl37, and these are the three different combinations that we can have. And as we said, the rarest isotope of chlorine of these two, the less common, is Cl37. So you would expect that Cl2 molecule with both chlorines as Cl37 will be the rarest, and we see that. We see that here because this has a relative abundance of 1. And here we've just compared the ratios, and we've cancelled the ratios down to their simplest form. Now here, because Cl35 is more abundant than Cl37, when we replace Cl37 with Cl35, so we have one Cl37 and one Cl35, we have a mass of 72. That's going to be more abundant than a molecule with a mass of 74, and that's what we see here, because relative abundance is 6. Now, the most abundant is going to be Cl, where both atoms in the molecule are Cl35, and that's going to be 9. So you always see in a mass spectrum of Cl2 the 9 to 6 to 1 ratio, where the relative abundance of 9 is a mass of 70, relative abundance of 6, mass of 72, relative abundance of 1, mass of 74. And this is why, and we need to revise this, it's best to memorize this so we can explain this in an exam. What about compounds with atoms that exists as different isotopes? So here we have a mass spectrum of a compound I'm going to designate this compound R. Within this compound, we have one atom of chlorine bonded within this compound. Now, this could be Cl35 or Cl37. Because there's only one chlorine, we don't have different combinations of Cl35 and Cl37. We can only have Cl35 or Cl37 in the compound. We don't have both at the same time. And this makes the mass spectrum more simpler to understand. So if you have what we call, and this is a molecule, so we can call these molecular ion peaks. Now, a molecular ion peaks is a molecule which is charged, and it has the charge of +1. And the molecular ion peak is at the highest mass to charge ratio because it has the highest mass. And so you can determine the mass of this molecule, relative molecular mass of this molecule. And the relative molecular mass, we've got two masses. One is 50, the other one is 52. And we would work out the relative molecular mass in the same way because the ratio of the small peak is 3 to 1 or 75% to 25%. The ratio is that. And so it follows this pattern as we would expect. And so when we see this pattern here in the molecular ion peak, then it does tell us that, or it does suggest that chlorine is present. And both of these are molecular ion peaks because they're both molecular ions. This peak here is not the whole molecule. It's a part of the molecule because the molecule has split into fragments, it's fragmented. But these two represent the whole molecule, one with Cl35 and one with Cl37. Normally, if there's not different isotopes, you will only have one molecular ion peak, but here you don't. So here we can see that this one contains Cl35 and this one contains Cl37. And the difference between the masses or mass to charge ratios is 2. And this is indicative of this. Let's look at a compound which contains one atom of bromine. And here bromine exists as two isotopes, Br79 and Br81, and they are equally abundant in nature. So in this compound, we have two molecular ion peaks. Now you may have seen the notation M+, that's the first molecular ion peak, and M+2, which is a molecular ion peak which is 2 mass to charge units greater than M+. And if you see this pattern where you have two molecular ion peaks which are equally abundant, and don't worry about the small difference here, we don't need to worry about that, that's insignificant, then it indicates that this compound contains bromine, and the M+ is a compound that contains Br79, and the M+2 molecular ion peak is the compound which contains Br81, and they are equally abundant because these isotopes of bromine are equally abundant. So they are incorporated equally frequently into these compounds. I hope you found this video useful. Please also check out my other videos on chemistry.